Going back over alloys, type of metallic solid. Okay. Alloys are combinations of two or more elements, the majority of which are metals. Adding a second or third element changes the properties of the mixture to suit different purposes. So there are many alloys out there, and they continue to create more based off of different purposes, what they need them for. And you will notice that there are a couple different types of alloys based off of the size. That there's the interstitial, the substitutional, based off the size of the atom as to where they go into the lattice structure. Okay, so we'll talk about some of these as we go along. Here is a table that shows you a couple different alloys on here, and you can see that they have their main primary metal, okay, and then addition of some other things to it, okay, and as you can see, like the bronze here is tough, chemically stable in dry air, okay, so that would be something you would want to be able to resist corrosion. Same thing with stainless steel here, whereas the plumber solder has a low melting point, okay, so that one's not, I would say, particularly tough. Dental amalgam, hopefully that these ones you have silver, some of them have mercury in them, okay, and you know, they put them into the teeth to fill in the teeth, and then they harden, those kind of things. So a bunch of different things up here showing some examples of common alloys and their purposes and their percentages of each particular element in there. Now, the two different distinguishing ones, substitutional versus interstitial. Substitutional alloys, second element is around the same size. It's not necessarily exactly the same size, but it's around the same size. And as you can see here, the example of up here, the substitutional one, 14 karat gold. Gold in and of itself is actually pretty soft. I mean, so they, in order to, of course, gold jewelry and other uses of gold, different size of the, like 18 karat versus 14 karat will depend on what other metals are in there. They also do other combinations to where you can have like the rose gold versus the white gold, those kind of combinations. But as you can see, 14 karat gold has silver in it too. It is not just all gold atoms. And silver and gold are similar in size, okay? The silver will be slightly smaller, but not like the interstitial alloy. The classic example of this one is steel. And lots of our buildings and boats and other things, cars, are made out of steel. Steel, the main component is iron. And then you have carbon atoms. So in the interstitial ones, you're going to have some of the smaller nonmetals and metalloids. It could be like boron, carbon, nitrogen, some of those in that row. Get put into the alloy, but they fill in the little spaces between the larger metal atoms. And as you can see here, we call them interstices. They are like the little crevices in between, which provides a lot of strength. It makes it a very structural, strong alloy. That's why we use it for so many things in terms of building materials. Now, alloys are typically stronger than the pure metal. Said the pure metal can slide, is malleable, you can form it into different shapes and everything. But you stick in some other ones there, they don't necessarily want to slide past each other as easily, so it does create a little bit more strength. But like I said, they do design them with certain percentages to make them have certain characteristics, certain properties, based off of the use of the alloy. Another thing is alloys typically retain the sea of mobile electrons, so the ability to conduct remains. And this is kind of where alloys fall in a gray area. So we say alloys are metal mixtures. That means it's a physical change. And you can separate them if you melt them down. You melt them down, melting point, you can separate them. However, If they're sharing the mobile electrons that can, the delocalized electrons, that's really like metallic bonding. So technically, they do some chemical bonding here, but we can still physically separate them. So that's where it's kind of a gray area, whether or not it's actually a chemical change or a physical change. You'll see it classified in most texts and on the internet as being a mixture, a physical change, but there is this gray area of, there is some metallic bonding occurring between the different metal atoms. All right, interstitial alloys. Atoms tend to make the lattice more rigid. Like I said, they fill in the little crevices there, okay? Decreasing malleability and ductility. And I highlighted steel because, like I said, that's the classic structural example for a really strong alloy. 99% iron here, 1% carbon, hard, strong, construction of buildings, cars, railways, bridges, those kind of things. But you can see some other ones up here, like pewter. Pewter is 96% tin, 3% copper, 1% antimony. And this one, pewter, like you have like serving dishes, lots of, I would say artistic type things are done in pewter because it's really shiny, it's lustrous, okay? Souvenirs, said some serving platters I have that are in pewter. Brass versus bronze, okay, up there you can see some more examples of those and their uses over here to the side. All right, so one other thing they touch on in this particular set of topic is large biomolecules or polymers. And we will briefly touch on them too when we talk about IMFs, because it also falls under that category. But in large biomolecules or polymers, non-covalent interactions may occur between different molecules or between different regions of the same large biomolecule. The functionality and properties of such molecules depend strongly on the shape, which is largely dictated by non-covalent interactions. And by non-covalent interactions, I'm talking about IMFs. And my examples up here, the main IMF is hydrogen bonding. And I'll go through and talk about them individually here. So we have the first example up here, DNA. And I'm sure a lot of you remember from biology that you have your A's, that the nitrogen bases, the A's adenine pairs with thymine, which is T, and the cytosine pairs with guanine, which is the C to G. But they make up that latter part of the double helix in DNA, but they are really held together. The nitrogen base is the middle part that makes up the ladder, all by hydrogen bonds. And that, of course, keeps the sequence of the code in the correct order because the code is used to generate the proteins, okay, that will give us our specific traits. So that's one region here where, it's linking. And the two on the left are biomolecules. They're like natural, of course. Second one here, I show the alpha helix in the protein. Alpha helix look kind of like a curly Q ribbon. Also held together by hydrogen bonds. This is like an O to an H here. Okay, and O to an H, O to an H. That keeps it in its curling fashion. Okay, so we have more hydrogen bonds here. There are also other proteins that fold differently. There's beta pleated sheets and a couple other ones out there. And proteins are functional based off of the way that they are shaped. Sure, you've heard or remember from bio that like enzymes are folded in a way so that their substrates can fit, so that they either can break apart or be put together very quickly, because enzymes are the biological catalysts. And other proteins too make up like the plasma membranes and organelles and other structural things in our cells and in our body. The problem is too, like if they are not folded correctly, they lose their functionality. So these intermolecular forces give them their functionality, and one way of, taking away the functionality of the protein is to denature it, either by heat, like, so they say if your fever gets too high for too long, then you're going to have some organ shutdown. I think that's because the proteins are being denatured. Also, pH levels, if those get too far off, that could also denature proteins. So they have to be folded specifically in order to work properly, and that falls under that homeostasis umbrella. Last but not least up here is nylon. Now this is more in the synthetic realm, a synthetic polymer, because all of these are polymers. They're very large molecules. They're made up of little tiny subunits called monomers, right? Nylon's one of the ones that's a synthetic one. PVC, that's polyvinyl chloride, that makes up the white pipes, things like that. A lot of our plastics, different grades of plastics, falls under this synthetic arrangement. But they are, like I guess you would say covalent solids, made up of course, the nylon, the PVC. Those are repeating units of long chains of hydrocarbons with different functional groups off of them. And they are also held together, as you can see, by some hydrogen bonds. But these are long chains of these subunits that repeat, and then you attach the long chains together, and then you get, you get nylon stockings and other uses. There's plenty of uses for nylon, and same thing happens with the plastics, and those are being held together by, our non-covalent interactions, these IMFs, that create some of, different types of, I guess in this way, the plastics and the PVC and all that, definitely solids. Okay. Now, I copied these off for you, so you can add them to your notes. They were meant to be in your notes to begin with, but these are very good tables that go over the different properties and are kind of comprehensive for you. So especially when you're working on your problem set, be a good thing to have out when you're trying to compare the properties. And yes, it's going to take a little while, and maybe you need to make some flashcards or do some cooking or whatever, because you really need to know like the key buzzword properties for each type of salad. You need to be able to recognize those. So, starting on the left here with the ionic, some of the key buzzwords, you're looking for high melting point. They are poor conductors or non-conductors in the solid form. Okay. Brittle. Brittle is a nice key word for ionic solids. Remember, if you shift them a little bit, then they start repelling, and they will have cleavage points, and they will flake apart. That's what brittle means. Okay. Relatively dense, dull surface. Okay. We're looking under molecular solids. One of the key ones is going to be low melting point. Okay. They're definitely poor conductors or non-conductors too. And they're soft. They have low densities, low melting points, soft. Okay. Like sugar and, some of those things in there where they're easily melted. The network covalent or covalent network ones here. Okay, keywords: high, super high melting point. Okay, very hard, very hard. Okay, they are poor conductors too, but they are the ones that are going to have extremely high melting points, and they're going to be very hard. Okay, the metallic ones are good conductors in the solid form, right? They do sometimes have varying melting points, because usually I'd say most metals have high melting points, but there are notable exceptions like mercury, gallium, some of these other ones that definitely don't fit that bill. Easily deformed under stress, so malleable, ductile, those are keywords for metallic solids. High density, lustrous, shiny, these are definitely the key buzzwords. You see those things, those are the context clues to let you know you're dealing with a metallic solid. Now I also like underneath here, they order the strength of the interaction. Molecular solids are always going to be the weakest because they are only held together by IMFs. IMFs are only sort of like partial forces. They're in between. They are definitely not as strong as your intra forces. Your intra forces are covalent, ionic, and metallic bonding. And the network covalent, which is a specialized type of the covalent bonding. The next will be ionic and metallic. They have like a squiggly mark between them because they are comparable in some ways to being kind of in the same range. Like I said, there's some metals that are definitely have really high melting points and are very strong. Ionic solids are always thought of being very strong, okay? But there's also some metallic solids that definitely would be weaker than the ionic solids. And in this case, usually what they do in that, if you're going to rank them, is they'll give you some kind of data point to rank them off of, like boiling points or melting points or hardness or something. They would give you some kind of data point in order to be able to rank those against each other. Obviously, over here on the far end, the network covalent are always going to be considered the strongest, right? And you do need to know them. There's really like only the 6 different examples that they will possibly give you, unless they don't already like reference it in the passage for you in an FRQ. But the ones you're looking for, like in multiple choice, or if they give you like a combination of 2 to select from, this is kind of like knowing your 7 strong acids. If you know these 6, then you know everything else that's going to be non-metal, or non-metal metalloid are going to fall under the molecular solids. So you're looking for C diamond. That's carbon, that's the diamond. Carbon, that's the graphite. Okay. The silicon compounds, silicon dioxide, your quartz. Silicon carbide. And the boron compounds, boron nitride and boron carbide. So silicon, boron, and carbon. These are the ones you're looking for that go into the network covalent or covalent network category. Anything else though, like carbon dioxide or sulfur or phosphorus, anything else goes into molecular solids. Okay? But if you know these 6, you can definitely distinguish the rest. Yes?
What is the last one?
It's B4C. This is boron carbide. So boron nitride, boron carbide. That's a 4. All right, know those, then you're good to go for the rankings. Yes?
The beige and green are the 6?
Those are the 6, yes. They are also already in the notes previously, but just make sure you're making clear notes that you need to know these separate as the covalent network, particular ones that they will ask you about.
What? So they're covalent network solids?
They're the super strong ones that are going to be different. Now, everything else, like I said, that's non-metal, or non-metal metalloid, those ones all go and now fall under molecular solids classification. Only these 6 you're going to put over in the covalent network.
C diamond?
Yes, that's carbon, that's the diamond, versus carbon, that's the graphite. Okay? So, one table. There's also the next table that I provided for you too. References a few other things in there, but a lot of it is the same. Okay? So, here we go.
Where's our colon between?
We have ionic solids up here. Relatively strong lattice of ions. Brittle, high melting point non-conductors in pure form. Conductors in water. You know, if you dissolve them, they can conduct. Metallic solids, malleable, ductile, good conductors. This one, 3D array of metal ions surrounded by the sea of delocalized valence electrons. Okay, covalent network, hard, brittle, high melting point, poor conductivity, or the semiconductors. The silicon and the boron, they fall under the semiconductor area. Okay. Many semiconductors are made of the metalloids because the metalloids have the components of both metal and non-metal, and the semiconductor components, they help us conduct the electricity without all the heat, because usually if you're conducting electricity through a metal, it gets really hot, and we know that heat really isn't good for our electronic devices, so we wanted to conduct the electricity without all the heat, and that's what semiconductors are good for. Molecular solids here, once again, soft, low melting points, non-conductors. See them all as like non-metal, non-metals, except for our 6 covalent network ones that I just told you about. Now, for the next 10 to 15 minutes, I'm going to have you work on all of the exercises, go through them, and then we will come back and discuss. All right, exercise 1. An ionic solid does not conduct electricity, but does conduct electricity when dissolved in water. Which of the following explains why? So this one was given in a diagram. Got to know this one. They like to ask it. Obviously, what has to be happening in order for us to be able to conduct electricity with the solid here? The ions need to be able to move. They need to be able to follow the charges. So that's going to be which one up here? C. C. Very good. So free mobile ions need to occur. That's why it does conduct when it's in the molten stage or liquid, because those IMFs have been overcome to where now they can move. And also when it's dissolved in solvents, polar solvents like water. All right, exercise 2. Energy required to dissociate ionic solid into gaseous ions is known as lattice energy. We have NaCl's lattice energy versus sodium oxide's lattice energy, which is much, much higher, 2500-ish. So, which explanation best accounts for this difference? It's going to be the magnitude of charge, okay? And you could also look for the fact that the chloride is going to be larger than the oxide. However, they say chloride has a smaller ionic radius than oxide. That's one that might catch somebody, and they might be thinking the reverse and mark A as because it's similar, sounds something like it should be, but it is completely incorrect. So yes, oxide has a -2. The sodiums are still going to be +1. So the magnitude of charge caused by that is going to increase the lattice, make the bond strength much larger. All right, now, which of the following would represent an ionic solid? Explain your choice. The one on the left or the one on the right?
Right.
The one on the right. Now, this is where people have struggled with, is the explanations. Explanations really need to stick to 2 to 3 sentences max, and you need to hit all of the lovely buzzwords. So, when we're talking about ionic, we need to mention, of course, the cation ions and the anions, or the positive and the negative ions. They are in an alternating pattern to maximize attractive forces and minimize the repulsive forces. So the right one does that better than the left one, because the left one, if you look here, it only alternates them across. As you go down the columns, they are all the same ion, and of course down the columns they would be repelling a lot more and have a huge amount of repulsions. So this is what I said. Nice, concise fashion. Ions must alternate to maximize coulombic attractions and minimize repulsions. The first diagram has alternating rows of oppositely charged ions, but the columns of like charged ions would cause huge amount of repulsions. There you go. Nice and concise. All right, exercise 4. Carbon steel is an alloy composed of a small amount of carbon atoms combined with iron. Consider the atomic radii of both carbon and iron and draw a model that describes the alloy that forms. So basically, you would formulate some kind of key. Okay, here's going to be my iron, and little ones over here be my carbons. So you want to draw, you know, the large ones, try to make them around the same size. I know I'm artistically challenged, but here I go. Then of course you would fill in some of the crevices with the carbons like so, and you would have drawing of steel. Luckily, I was able to find a nice graphic which represent that here too. In this case, green is representing the iron and the blue would be the carbons. Yes?
Do the irons have to be touching?
No, they can just be like kind of right next to each other like so. There's usually a little bit of space, tiny bit of space between, because, you know, it's a row of these, you know, positively charged nuclei cations with the delocalized electrons. So the only other thing I will say though about drawing metallic solids or alloys You never ever put like charges on them. The only ones that's gonna show like the charges are gonna be the ionic solids because alternating pattern of cation, anion. So these guys are gonna be solid. You just make up a key and go with it. So like here, yes, this is a picture of an alloy where I think that they spaced them a little too much. They probably should be a little bit closer, but labeling here, the left diagram, what's that one? That's the pure metal, right? Because it's all the same color atom there. The one in the middle we would call substitutional. They're slightly smaller, but within range of being around the same size. And then over to the right, the interstitial. Okay. Being able to recognize those, once again, these ones don't have any charge on them. The ones that have charges will be ionic. Okay. And you'll notice definitely the same kind of pattern. Like you got to recognize the diagrams. You love to ask questions using the diagrams. All right, this one's a good one. This one was actually in an FRQ. Okay, so not this exact problem, but one similar to it I've seen. 2018, scientists engineered an alloy composed of platinum and gold, which is 100 times more wear resistant than stainless steel. 90% is platinum, 10% is gold. Sketch a model of 20 atoms indicating whether this is interstitial or substitutional. Use the correct ratio of atoms to be sure. Now, look here, platinum and gold. It's definitely going to tell us which type of alloy we're drawing. If you look at the periodic table, platinum and gold are right next to each other, so this one's definitely going to be what? Substitutional. Okay, so this one's substitutional. Now, I have to draw 20 atoms, and 10% of them need to be gold. So, 20 or 10% of 20 means how many are going to be gold? That looks terrible. Hold on, let me rewrite this. So we have 20, we need 10% of this. It's going to be gold, so that means 2 of them need to be drawn as gold. That means the other 18 need to be the other 18. Very good. And then you draw yourself a little key, like so. So I'm going to make the platinum versus the gold, like so. So I would stick to doing 4 rows of 5 or 5 rows of 4. Okay? So 1, 2, 3, 4, 5, 2. Put in a gold somewhere in here. 3, 4. 1, 2, 3, 4. And so you must have the 20 count, and you must have 2 of them switched out for the gold. Obviously much easier to do when you have nice little circle graphics, but there you go. And I even made the gold just a little bit tiny smaller because technically it is because it has 1 more proton pulling in that electron cloud just slightly. All right, pure metal and interstitial alloy contain the same metal were examined. Predict which substance will have a greater density. Greater density, okay, in your selection. Obviously, should pop out to you which one's going to have the greater density. The alloy, because within the spaces in between, we're going to be filling that with more matter, right? More matter goes in, then you have more matter packed within the same space. Obviously increasing the density. So density, remember, is mass over volume. The interstitial alloy is going to have more mass because you have more particles packed into those spaces. The regular pure metal is just going to have those spaces empty. So the same volume though, if we're talking about the same space here, okay? So greater density is the interstitial alloy. Spaces in between the metal is filled with smaller atoms like carbon, nitrogen, boron, etc., which adds to the mass but leaves the space of the atoms the same. Larger mass and the same volume, of course, gives you a larger density. And if you're going to refer to the density equation, to that, you definitely need to insert it somewhere. Okay? So I would do that. Make sure that you insert it somewhere. All right, exercise 8. We have carbon dioxide's melting point and silicon dioxide's melting point. So let's first do A, identify the type of solid that each substance forms. So for CO2, what's that one going to be? Molecular, good. Molecular. All right, solid and our SiO2. Because we definitely know and have memorized now that silicon ones are going to be covalent network. Now this is where, of course, the justify part, it's always fun, justify the difference. So you need to talk about the fact that CO2 is held together by what? INS, which are much weaker than covalent network bonds, the covalent bonds in the lattice structure of the covalent network solid. So yes, that would be what you would need to state there. So since CO2 is a molecular solid, only weak IMFs. Technically they're LDFs because CO2, remember, is linear and it's nonpolar. You don't really have to include that, but I did. Will be overcome to separate the molecules. SiO2 is covalent network with very strong covalent bonds that require a large amount of energy to break, giving a much higher melting point. So definitely mention the weak IMFs versus the strong covalent bonds of the lattice of the covalent network. Very good in the explanation there. But notice these are not, those explanations are sticking to 2 to 3 sentences, not going way over. All right, so determine the type of solids that matches the description. Here you're looking for the context clues. So metallic atoms with loose electrons. I don't even have to read further from sea of electrons. Sea of electrons tells me what? Metallic. Gotta be metallic. All right. Non-metal atoms form molecules with covalent bonds. They are held together by intermolecular forces. Molecular. So I'm looking for these context clues to distinguish between them. Aha! I don't know if I have to read much further than metal and non-metal atoms forming a lattice. It still goes positive, negative. At that point, I know I'm talking about ionic. Very good. Like so. And the last one here, non-metal atoms form lattice structure held together with covalent bonds. Lattice one with covalent bonds has to be? So covalent network. Very good. Covalent network. All right, we're getting there. Last but not least, identifying them from their formulas. Okay? What type of solids will each of the following substances form? So benzoic acid. That's molecular. We got all nonmetals, but it doesn't fit the 6 that are in the covalent network category. So I agree. This one's going to be molecular. All right. B4C, boron carbide. Network covalent or covalent network, doesn't really matter. Gold. Metallic. It's just a metal, so it's got to be metallic. Very good. How about potassium chloride? Ionic. Very good. And glucose, C6H12O6. Molecular. You're getting good at this. Good. And calcium bromide. Ionic. Good. Silicon carbide. Network covalent. Very good. Recognizing those. And phosphorus. Molecular. There's a couple different allotropes of phosphorus. P4 happens to be one of them. Molecular. And brass, which is a combination of zinc and copper. Metallic. Technically it falls under alloy too, so depending on the choices they give you, you could also write alloy. And be specific about that. Yay, and we are